Hello and welcome to today's video where we're going to talk about set building notation. So this is kind of where we create rules and use variables to describe and help us build a set. This can allow our sets to be more flexible and more easily understood. This is a really important part of developing your understanding of sets and being able to add that flexibility and really create new sets of things that aren't just the standard natural numbers, integers, things like that. And remember, we actually had trouble representing the rational numbers, and that's where we're going to start here with this set builder notation. So remember Q, that was the set of all rational numbers. Rational numbers are just any number that can be represented by a fraction. So before we learned set builder notation, we were kind of struggling. We were saying, well, it's 1 over 1, it's 1 over 2, because we can't really find a pattern here. It's 1 over 3, but it's also 2 over 3, right? So you can increase on both the top and the bottom. But when I see this set, if I didn't see the Q and know it was rational numbers, I would be really confused at the pattern they were trying to get at here. So this is not the way we want to do this. We want to use set builder notation. And so the general set builder notation formula, so let me see, I'll write this down here. So set builder notation, we have a rule, so we say some rule here, some formula usually. Then we do this little line right here, and then we give the conditions. So conditions for variables, and note that the rule contains these variables and then we put some conditions on them. So, and it's not just a single variable, it can be multiple. So in this line right here, you read that as such that. So let's just see what this means. So let's do this here. So set builder notation for Q. I want to show that all fractions so every number that can be written as a fraction is a rational number. That's what I'm trying to represent. So what I'm going to do is I'm going to say, well, a fraction, I'm going to have some variable m divided by some variable n. That's my rule. That's that right there. And then now I'm going to say such that. And now what are the conditions of m and n? Well, m can be any number, right? It can be 0, 1, negative 1, 2, 3, 4, so on and so forth. Well, those are integers, aren't they? So m. And then n is also the same thing with one exception. Try to think of that exception here. So n is also all integers except for 0, right? Because you can never divide by 0. So I'm going to say, so m and n, and then now remember that symbol that we talked about in the first video in Introduction to Sets, we said is an element of. That's what we're going to need to do here because m and n are elements of z. Remember, z are integers. That's one of those important sets that we need to know. The z is the integers. And n cannot be 0. So n does not equal 0. So these are our conditions here. So these are the conditions for the variables where that was our rule. And this is the way we represent rational numbers. This is the efficient way to say the rational numbers. If you think about this compared to what we had here with 1 over 1, 1 over 2, 1 over 3, 2 over 3, this is much more clear. Now I know what you mean here because it's m divided by n. M and n can be integers as long as n is not 0. I think about that for a second and I can see, okay, that's the set of all fractions. And it's going to exclude 0 because you can't divide by 0. So now we have a much better way to express kind of what this set is, and that's using set builder notation. So this is an important thing to know, and let's do some practice questions right here. So now this is a different example. This is not necessarily like mathematical, but it really shows you what I mean with this set builder notation and its flexibility. So consider creating a set for things on your bedside table, and write the set in set builder notation. So the bedside table currently is the alarm clock, the phone, and the wallet. So I'm going to draw that. Let's say this is my bedside table. I've got alarm clock, I've got my phone, I've got my wallet. But I want my set builder notation to show that if I add something to my bedside table, that needs to be added to the set. So I can't just say the bedside table equals alarm clock, phone, wallet. I want it to be a little more flexible. So I'm going to say that bedside table, I'm going to write that as BT, equals. So now again, let's think about this. The formula is rule first. So what is the rule going to be? Like the formula here. I'm going to say just x. Then the condition such that x is on the bedside table. On the bedside table. So this is now in set builder notation. The condition for x is just that it's on the bedside table. So anytime I add something to the bedside table, let's say I added my keys maybe, that would automatically map that onto here, and this formula is more flexible now. So in a program or something like that, you would assign something a group, and it would be called bedside table, and this would automatically add it to the group, the other kind of part that might be called something different other than bedside table. Let's just say bedroom or something. That might be a better way to do this, but for this example, that's what it is. So you'd say X, given that X is on the bedside table, and it'll map it straight to the group just like that. So that's another way set builder notation helps us with that example. Let's look at one more. So create a subset containing the positive odd integers using set builder notation. So the first thing I'm going to do is I'm going to write down what numbers am I trying to get in this set. The positive odd integers, so I know I'm getting 1, 3, 5, 7, so on and so forth. Okay, so those are the numbers that I need to somehow have in my set. And whenever I think of odd numbers, let's think of the kind of the formula for odd numbers and odd integers. It's 2n plus 1. N is just any number or integer. So because 2 times any number is even, and then we add 1 to get to the odd. So that makes sense. But now let's think, how do we get it to where this includes everything? So I'm going to write, let's name our set A. So A equals, what's our rule going to be? Well, I'm going to say it's 2n plus 1 because it's odd numbers. So now it's positive odd numbers though. So now the conditions on n have to somehow exclude when n is negative. But they have to include 0, right? Because when n is 0, I get to that first 1 because it's 2 times 0 plus 1 equals 1. So what kind of set do I need to write to have it include 0 but not include anything else? It can't include -1, it can't include -2, but it includes 1 because that'll give me the 3, and then 2 times 2 plus 1, that'll give me the 5, and you see so on and so forth. This is going to give me the pattern I need. That's why the rule is 2n plus 1. But now the condition is kind of the hard part here. So I need the numbers. I need somehow to write a condition that includes 1, 2, 3, 4, so on and so forth. It needs to include that pattern. But I see this right here is the natural numbers, right? The counting numbers. So that's what I'm going to use. The 1, 2, 3, 4, 5, 6, 7. So n is an element of n, big N. Because remember, big N represents the counting numbers, the natural numbers. So this is natural numbers. But there's one problem with the natural numbers. They do not include 0. So n is an element of n, or n equals 0. And that includes the whole set. So n can be a natural number, or n can be 0. And if either of those two things happen, then I can include it in the set. And that's what gives me this new set here, where that is the set of positive odd integers using set builder notation. So hopefully that makes sense. Hopefully now you can really understand the flexibility that you're going to have if you learn how to use this set builder notation. I think an important thing to know that n is the natural numbers, know that z is the integers, and q is the rationals, because they're going to keep coming up again and again, and you can't even do set builder notation without those sets because you often have to reference them when you're saying n is an element of the integers, so on and so forth. Thank you for watching, and let me know if you have questions. Have a good one.